Hi, this is Mr. Yeager, going to look at a topic very briefly today. Um, we have to look at Einstein's view of gravity. So obviously we've covered what is gravity in terms of from a Newtonian perspective. Obviously a force between two objects with mass. But when Einstein came along, he developed a different view of how gravity actually works. That also includes how Newton's explanation, basically, of why Newton basically believed what he did with gravitational force. So, with Einstein's view of gravity, what he defined is gravity causes an effect to space and time. He says he causes it to affect space and time around it. What we really basically can narrow this down as, especially with the idea of space, is gravity essentially will curve space. All right? And so what we really mean by that, and there's a good video that you should watch as well, that in this unit found on its learning. Of somebody showing gravity, the idea of gravity, how it will bend space. And what we mean by that is, instead of thinking of space as basically flat, okay, we're walking through space. When a mass goes on that space, what it will do is it actually curves that space around it, okay? It creates that curvature around it. And the idea is, especially, obviously, we are all doing this, but planets do it more. Larger objects will curve space more. This is what Earth is doing. Earth curves the space around it, and what's happened is the moon is caught in that curvature of that space, making it go around and around and around. Okay? And it'll rotate, and because it has that velocity, it doesn't have any friction, it can keep on moving around in that space and not be pulled any closer down. What I sometimes relate this to is it's similar to those, and I don't know how much they're around anymore. There used to be those big bowls that you put a coin in, and the coin would zip around and around and around and around and around, and eventually going into the hole at the bottom and collect all the coins. Okay, it's the same idea of what gravity, what a mass is doing, and what its gravity is doing to that space around it. It is curving it. It's making it bowl-shaped. Again, we want to see this as not only just simply a curve in a two-dimensional space, but it's three-dimensional and all around the whole object. It's curving the whole space around the sphere of the object itself. Okay, so it's almost like two bowls on top of each other. And so the thing is, how did we come up with this? I mean, it helped us make sense of why things attract, because we could say, you know, if the moon was not moving, I'll go to a new page real fast. Okay. If the moon was not moving and you got this bowl around, the curved bowl around the Earth, basically what you'd see happen is, well, the moon would be attracted to that curvature of the Earth and go straight toward the Earth, which is what we're doing. We're constantly attracted to this curvature and brought down into it. We're obviously very small compared to the moon. Okay? But that's basically what is going on with Einstein's view. He believes that space is curved. Okay? It's a effect on the space around it. Okay? And so the thing is, one way we know that this, or we should say, supports this idea of curved space, all right, is that light actually bends with the curvature of space. Okay? We'll get more into how light moves around, but we basically say light moves fast enough that it should move in straight lines. All right? The thing is, it turns out when light passes a planet, it basically will curve and basically start going around the planet instead of going straight by as we would expect. We would expect the light to go straight by the Earth. But it turns out that light actually will curve as it passes by the Earth or any other planet. And this is something that we've actually astronomically seen with telescopes and everything else like that. that we actually can see that the light is curving around different planets, okay, and different, obviously, objects in outer space. So that's one of the biggest things. So light bends when it passes planets. All right. And so we've used this to help us do a couple different things. All right. This idea has actually helped us figure out the distances to different stars. So I'll write down uses of this idea. We figured out distances to stars. It helps explain black holes. All right. The idea of a black hole is such a massive object, such a dense, massive object that's creating such a deep bowl in space-time that the light basically can't escape it and never comes out. Most of the time, basically think of you have a curved surface and you shoot something across it, you throw a marble, it should curve some, but it will probably fly off the table. A black hole is so deep that even if I shoot something really fast across it, it'll start eventually, it would never fly off the table, it'll curve going down into the bottom of the bowl. Okay? So dynamics of black holes have basically been supported with this idea. We want to also say satellites and GPS use this idea as well, because if you think about it, okay, I'm going to go and erase some of this stuff. If you think about it, we have this planet, we have Earth. Oh, can't spell Earth. We have planet Earth, and there are satellites all around the Earth, all on different sides of the planet. Now, there's a couple different ways that these signals can obviously be sent. What if a satellite wants to communicate with the satellite on the other side of the planet? All right. Well, it sends these radio signals and other forms of light waves. Radio waves is a form of light. It travels at the speed of light. It is light. Okay, it's just in a different wavelength. The thing is, it's moving so fast that we normally say that this would go straight off into space, and we'd never get that signal to the other side of the planet. The thing is, obviously, there's a couple different things going on here. There's probably other satellites, but again, they're around the curvature of the Earth. But the idea is the signal will be able to curve around the Earth some. Okay. Again, we'll have to bounce off multiple satellites because that signal will definitely go off straight. Earth is not strong enough to just simply suck the light in. All right. But it uses that idea as well. So supporting this idea of Einstein's idea of gravity are things like how we've measured astronomical distances, GPS signals, how we use those to do obviously communication all the way across the planet, and then black hole dynamics as well. All right. So now we get to one last, obviously very strange topic. Okay, is with this idea with gravity. Okay, we say gravity will bend what's called space-time. Okay, we are always walking around in this Earth through what's called space-time. All right. Now, the space is kind of easy to understand how we bend that. We can think of the bowl, okay? But the thing is, this is where Einstein developed this idea of theory of relativity of time is also relative to our perception, how we perceive it, what we are doing. And obviously, what I usually say with students is, your perception of time is dependent upon the light that you see. You see something occur because it occurs in the light. Okay? It is sensed in that form with light. All right? So my big thing is, all right, what if, all right, this is kind of like a thought experiment. What if one person, you have a second person that's able to see that light before you do? Okay? What would happen here? What would we say is occurring? Okay? And basically you'd say that this person sees the occurrence before the other one. Okay? Sees what is happening before the other one, and maybe this person then goes, hey, wait a minute, you've seen the future. Okay? And therefore, hey, have you time traveled? Obviously no. Okay? But it has to do with who is obviously perceiving that light first. And I don't want to sit here and be like, oh, it's because you're sitting in the back of the classroom. It has to do with your motion. Okay? And it turns out as you increase velocity, time slows down for you. Okay? Time will slow down for you. And that's because it turns out light must stay a constant speed of 3 times 10 to the 8th meters per second faster than you at all times. So the thing is, if you're speeding up, that means one of these two factors, distance and space, actually both of them, must adjust, must bend, must squeeze more for the person that goes faster. And so the idea is eventually, theoretically, if you travel the speed of light, time will stop. Okay? Because the idea is, if you're going that fast with the speed of light, that's what time depends on. If you're matching that, basically you are ahead, not ahead of time. You are at a point where time is no longer moving. It is done. Okay. And so the last thing I basically want to show you is there's a graph from a good video that I watched I always share with students in the classroom. Okay, where they basically make a graph of space-time, space versus time. Okay? And again, you can basically say this is meters versus seconds. So the slope of the line is velocity. Okay? The thing is, we basically all travel down here. I mean, this right here would basically be you're in a jet going the speed of sound. I mean, so what you can see here is as you're traveling through space, time is moving basically with you exactly as you go along. But the idea is, if you go even faster, if you're going even faster through time, you speed up, you have a higher velocity. Okay? What happens is time has to be going a little bit slower. You're perceiving time more slowly. This person will see 5 seconds at this point, but you're not going to see it until up here a little bit later. Okay? And so the idea is if you're traveling through space at 3 times 10 meters per second, which would be straight up on the space, you're basically traveling through it immediately. That's where time is now 0 and it will not change. So obviously the crazy thing is, as people say, is what happens if you go faster than the speed of light? Technically, you go into the negative time zone, which that's just kind of getting us ridiculous here. It's difficult to really explain and go, okay, well, what's going to happen? It's basically impossible. People basically say it's theoretically impossible to go faster than the speed of light because light must always travel this much faster than you. Even if I'm going 3 times 10 to the 8th meters per second, light will be traveling 3 times 10 meters per second, 10 to the 8th meters per second faster than me. But you're going, oh my gosh, what? But it can't, what is going faster with it? So I know at the end there it get a little crazy. All right, time travel is a very funky idea. The main idea is to get from this short lecture is really, again, that Einstein's view of gravity. It bends space, it bends time, it can manipulate both. And then some of the uses for, or ways that we've shown light being bent in terms of GPS, astronomical distances, and black hole dynamics as well. All right, thank you very much.